So good afternoon everyone. My name is Mike Angelo Magalona and today I'll be discussing to you about linear programming. Our topic for today is simplex maximization method containing equal symbols. Our learning outcomes for this topic are: in this section, you will learn to solve linear programming maximization problems using the simplex method. First is to identify and set up a linear program in standard maximization form. Second, convert inequality constraints to equations using slack variables. 3. Set up the initial simplex tableau using the objective function and slack equations. Lastly, identify the optimal solution from the optimal simplex tableau. Let us first define what is simplex maximization method. The simplex method is utilized to solve linear programs. A need to solve linear programs arises in finding answers to problems of planning, scheduling, assignment, location, network flow, and many other kinds, which arise in manufacturing, distribution, transportation, systems, finance, and many other fields. Let me give you a short background about the simplex method. So the simplex method was developed during the Second World War by Dr. George Dantzig. His linear programming models helped the Allied forces with transportation and scheduling problems. In 1979, a Soviet scientist named Leonid Kachyan developed a method called the ellipsoid algorithm, which was supposed to be revolutionary. But as it turned out, it is not better than the simplex method. In 1984, Narendra Karmarkar, a research scientist at AT&T Bell Laboratories, developed Karmarkar's algorithm, which has been proven to be 4 times faster than the simplex method for certain problems. But the simplex method still works the best for most problems. Moving on, these are the steps to do when using the simplex maximization method. First step is to set up the problem. This is to write the objective function and the inequality constraints. Number 2. Convert the inequalities into equations. This is done by adding one slack variable for each inequality. Number 3. Construct the initial simplex tableau. Write the objective function as the bottom row. Number 4. The most negative entry in the bottom row identifies the pivot column. Number 5. Calculate the quotients. The smallest quotient identifies a row. The element in the intersection of the column identified in step 4 and the row identified in this step is identified as the pivot element. The quotients are computed by dividing the far right column by the identified column in step 4. A quotient that is a 0 or a negative number or that has a 0 in the denominator is ignored. Step 6. Perform pivoting to make all other entries in this column 0. This is done the same way as we did in the Step 7. When there are no more negative entries in the bottom row, we are finished. Otherwise, we start again from step 4. And lastly, read off your answers. Get the variables using the columns with 1 and zeros. All other variables are 0. The maximum value you are looking for appears in the bottom right-hand corner. Moving on, let us solve this sample word problem. Nikki holds 2 part-time jobs, job 1 and part 2, and job 2. She never wants to work more than a total of 12 hours a week. She has determined that for every hour she works at job 1, she needs 2 hours of preparation time. And for every hour she works at job 2, she needs 1 hour of preparation time, and she cannot spend more than 16 hours of preparation. If she makes $40 an hour at job 1 and $30 an hour at job 2, how many hours should she work per week at each job to maximize her income? So our solution for this problem, we will follow the algorithm listed above. Step 1. Set up the problem. Write the objective function and the constraints. Since the simplex method is utilized for problems that consist of many variables, it is not practical to use the variables x, y, z, etc. Hence, we use symbols like x sub 1, x sub 2, x sub 3, and so on. So, let x sub 1 be the number of hours per week Nikki will work at job 1, and let x sub 2 will be the number of hours per week Nikki will work at job 2. Note that it is customary to choose the variable that is to be maximized as z. Hence, the problem is formulated as maximize z is equals to 40x sub 1 plus 30x sub 2, which is subject to x sub 1 plus x sub 2, which is less than or equal to 12. 2x sub 1 plus x sub 2 is less than or equal to 16. X sub 1 is greater than or equal to 0, and x sub 2 is greater than or equal to 0. Step 2. Convert the inequalities into equations. This is done by adding one slack variable for each inequality. For example, to convert the inequality x sub 1 plus x sub 2, which is less than or equal to 12, into an equation, we add a non-negative variable y sub 1, and we get x sub 1 plus x sub 2 plus y sub 1, which is equal to 12. Here, the variable y sub 1 picks up the slack, and it represents the amount by which x sub 1 plus x sub 2 falls short of 12. In this problem, if Nikki works fewer than 12 hours, say 10 for example, then y sub 1 is 2. Later, when we read off the final solution from the simplex table, the values of the slack variables will identify the unused amounts. Next, we write the objective function. Z is equals to 40x sub 1 plus 30x sub 2 as negative 40x sub 1 minus 30x sub 2 plus z is equal to 0. After we add the slack variables, our problem reads the objective function negative 40x sub 1 minus 30x sub 2 plus z is equal to 0. Our subject constraints are x sub 1 plus x sub 2 plus y sub 1 is equal to 12. Next is 2x sub 1 plus x sub 2 plus y sub 2 is equal to 16. Hence, our x sub 1 and x sub 2 will be greater than or equal to 0. For our step 3, construct the initial simplex tableau. Each inequality constraint appears in its own row. Write the objective function as the bottom row. Now that the inequalities are converted into equations, we can represent the problem into an augmented matrix called the initial simplex tableau as follows in the diagram below. Step 4. The most negative entry in the bottom row identifies the pivot column. Hence, the most negative entry in the bottom row is negative 40. Therefore, the column 1 is identified. For step 5, calculate the quotients. The smallest quotient identifies a row. The element in the intersection of the column identified in step 4 and the row identified in this step is identified as the pivot element. Following the algorithm, in order to calculate the quotient, we divide the entries in the far right column by the entries in column 1, excluding the entry in the bottom row. So as you can see, the number 12 is divided by 1. The far right column is divided by the entry which is the column 1. So 12 divided by 1 is equal to 12. And 16 divided by 2 is equals to 8. Step 6. Perform pivoting to make all the other entries in this column 0. Pivoting is a process of obtaining a 1 in the location of the pivot element and then making all other entries zeros in that column. So now, Our job is to make our pivot element a 1 by dividing the entire second row by 2. The result follows. To obtain a 0 in the entry first above the pivot element, we multiply the second row by -1 and add it to row 1, and we get this equation. Hence, to obtain a 0 in the element below the pivot, we multiply the second row by 40 and add it to the last row. As you can see, there are some changes in the last row. The -40 is changed to 0, the -30 is changed to -10, the y sub 2 column, which is 0 in the last row, is changed to 20, and in the far right corner, which is supposed to be 0, it is now in 320. We now determine the basic solution associated with this tableau. By arbitrarily choosing x sub 2 equals to 0 and y sub 2 equals to 0, we obtain x sub 1 equals 8 and y sub 1 equals to 4, and z is equals to 320. If we rewrite the augmented matrix, whose left side is a matrix with columns that have 1 and all other entries zeros, we get the following matrix stating the same thing. In step 7, when there are no more negative entries in the bottom row, we are finished. Otherwise, we start again from step 4. Since there is still a negative entry, which is the -10 in the bottom row, as you can see in the x sub 2, we need to begin again from step 4. This time, we will not repeat the details of every step. Instead, we will identify the column and row that gives us the pivot element and highlight the pivot element. The result is as follows. So the 4 in the far right column is divided by 1/2, since the x sub 2 is the entry, which is the entry column, which is supposed to be 4 divided by 1/2 is equals to 8. And next is 8 divided by 1/2 still is equals to 16. We make the pivot element 1 by multiplying row 1 by 2, and we get the following answer. Now, to make all the other entries as zeros in this column, we first multiply row 1 by -1/2 and add it to row 2, and then multiply row 1 by 10 and add it to the bottom row. As you can see, there are no more negative numbers as you can see in the table below. Step 8. Read off your answers. We now read off our answers. That is, we determine the basic solution associated with the final simplex tableau. Again, we look at the columns that have a 1 and all other entries zeros. Since the columns labeled y sub 1, y sub 2 are not such columns, we arbitrarily choose y sub 1 is equals to 0 and y sub 2 is equals to 0, and we get the following equation. X sub 1, its values will be 0, 1, and 0. And x sub 2, its values will be 1, 0, 0. In z, in its column are 0, 0, 1. And for c, its numbers included in that column are 8, 4, and 400. Hence, the matrix reads x sub 1 is equals to 4, x sub 2 is equals to 8, and z is equals to 400. The final solution says that if Nikki works 4 hours at job 1 and 8 hours at job 2, she will maximize her income to $400. Since both slack variables are 0, it means that she would have used up all the working time, as well as the preparation time, and none will be left. And I hope you learned something in our word problem number 1. Now let's move on to our sample word problem number 2. A manufacturer produces 3 types of plastic fixtures. The time required for molding, trimming, and packaging is given in the table below. Times are given in hours per dozen fixtures. So these are the types of processes, the 3 types: molding, trimming, and packaging. For in type A, the given data is 1 for the molding, 2/3 for trimming, and 1/2 for packaging. And the type For type B, the molding time in hours is 2, trimming 2/3 as usual, and for packaging it will be 1/3. In type C, the, the time is 3 halves, in trimming 1 and packaging 1 half. The total time available in molding is 12,000, in trimming 4,600, in packaging 2,400. For its profit, type A will have $11, in type B $16, and type C $15. Our question is, how many dozen of each type of fixture should be produced to obtain a maximum profit? Our solution is, letting x sub 1, x sub 2, and x sub 3 represent the number of dozen units of types A, B, and C respectively. The objective function is given by profit, which is, we can assume that it is P, is equals to 11 x sub 1 plus 16 x sub 2 plus 15 x sub 3. Then the numbers, we were raising them in the profit, which is 11, 16, and 15. Moreover, using the information in the table, we construct the following constraints. X sub 1 plus 2x sub 2 plus 3 halves x sub 3 is less than or equal to 12,000. 2 2/3 x sub 1 plus 2/3 x sub 2 plus x sub 3 is less than or equal to 4,600. And 1 half x sub 1 plus 1/3 x sub 2 plus 1 half x sub 3 is less than or equal to 2,400. We also assume that x sub 1 is greater than or equal to 0. X sub 2 and x sub 3 are also greater than or equal to 0. Now, applying the simplex method with the basic feasible solution. Now, we can assume that x sub 1, x sub 2, x sub 3, s sub 1, s sub 2, s sub 3 is equals to the values 0, 0, 0, 12,000, 4,600, and 2,400. Thus, we obtain, in x sub 1, we obtain the values 1, 2/3, and 1 half. X sub 2, which is 2/3, 2, 2/3, 1, and 1/3. For x sub 3, we have 3 halves, 1 and 1 half. For s sub 1, we have obtained 1, 0, 0. For s sub 2, we obtain 0, 1, 1. And for s sub 3, we obtain none, which are all zeros. And let b is equals to basic, and v is the value of the profit, which is 12,000, 4,600, and 2,400. Hence, for step 2, we obtain the entry column. And for this step, the column x sub 1 is the entry column. Hence, the values are changed. Basically, for a while ago, the values now in x sub 1 are 1 half, 1/3, and 1/3. In x sub 2, there are some changes, 1, 0, 0, and x sub 3, 3/4, 1 half, and 1/4. For s sub 1, 1 half, negative 1/3, and negative 1/3. In s sub 2, we obtain 0, 1, 0, s sub 3, 0, 0, 1, and for b, we have 6,600, 400, and its total is 96,000. The next column is the x sub 3. The values are now changed again. In x sub 1, we have 0, 0, 1, x sub 2, 1, 0, 0, x sub 3, 3, 8, 1/4, and 3/4. S sub 1, we have 3/4, negative 1, 6, and negative 1 half. S sub 2, we have 0, 1, 0, S sub 3, negative 3 halves, negative 1, 3. And for our b, we have 5,400, 200, and 1,200, and its values are now changed, which is 99,600. Next step is to cancel the negative in the last column. Now the values are now changed. For x sub 1, x001, x sub 2, 100, x sub 3, 010, s sub 1, 1, negative 2/3, 0, s sub 2, negative 3 halves, 4, and negative 3. For S sub 3, we have 0, negative 4, and 6. For B, we have 5,100, 800, and 600. For S sub 1, as we look at here, there is a negative value, which is the negative 3/4. Now, as you can see, there are no negative values in the last column. Hence, our total in the B is 100,200. From the final simplex W, we see that the maximum profit, which is $100,200, and this is obtained by the following production levels. Type A, which is 600 dozen units, Type B, which is 5,100 dozen units, and Type C, which is 800 dozen units. Now moving forward to our last sample word problem. Luminous lamps produces three types of lamps, A, B, and C. These lamps are processed on three machines which can be assumed as X, Y, and Z. The full technology and input restrictions are given in the following table below. So our product, which is A, B, and C, and our machine, which are X, Y, and Z, and the profit per unit. The profit per unit, the XYZ has as data in column A we have 10, 7, and 2, which its proper profit per unit is 12. In product B, its data is 2, 3, and 4, and its profit per unit is 3. And in column C, its data is 1, 2, 1, and its profit per unit is 1. And the available time for each machines are: for machine X, it has 100, machine Y has 77, and 80 for the machine Z. Our question for today is: find out a suitable product mix so as to maximize the profit. Our solution for this problem is: the decision problem can be formulated as maximize Z is equals to 12x sub 1 plus 3x sub 1 plus x sub cube. We are basing them from the profit per unit, which are 12, 3, and 1, which are subject to 10x sub 1 plus 2x sub 2 plus x sub 3, which is less than or equal to 100. 7x sub 1 plus 3x sub 2 plus 2x sub 3, which is less than or equal to 77. And 2x sub 1 plus 4x sub 2 plus x sub 3, which is less than or equal to 80. We can denote that x sub 1, x sub 2, and x sub 3 is greater than or equal to 0. Next is, let us convert the inequalities to equalities. Then x sub 1 plus 2x sub 2 plus x sub 3 plus x sub 4 is equal to 100. Pardon for the error in the PowerPoint presentation. Next is 7x sub 1 plus 3x sub 2 plus 2x sub 3 plus x sub 5 is equals to 77. 2x sub 1 plus 4x sub 2 plus x sub 3 plus x sub 6 is equals to 80. Hence, x sub 1 up to x sub 6 are all greater than or equal to 0, where x sub 4, x sub 5, and x sub 6 are slack variables in this problem. Including these slack variables in the objective function, we get maximize Z, which is 12x sub 1 plus 3x sub 2 plus x sub 3 plus 0x sub 4 plus 0x sub 5 plus 0 sub 6. There are all zeros because there is these three, which 4, 5, and 6 are just slack variables. They are not included in our data. And next is our initial basic feasible solution. X sub 1, which is equal to 0, x sub 2, x sub 3 is also equal to 0, and Z is equals to 0. Our x sub 4 is equals to 100, x sub 5 is equals to 77, and x sub 6 is equals to 80. We just interchange our data in this initial basic feasible solution. Hence, we have our table 1 here. Our basic variables, which is B, has this x sub 4, x sub 5, and x sub 6. The 12, 3, 1, 0, 0, 0 are the values of our x sub 1 up to x sub 6. In x sub 4, we have 10. In In x sub 1 we have 10, in x sub 2 we have 2, in x sub 3 we have 1, x sub 4 we have 1, x sub 5 0, and x sub 6 we have 0. Hence our solution values, which is b multiplied by x sub b, is equals to 100. For our next column, our x sub 1 and x sub 5 has 7, x sub 2, x sub 5 is 3, x sub 3, x sub 5 is 2, x sub 4, x sub 5 is 0, x sub 5, x sub plus, and x sub 5 have 1, and x sub 6, x sub 5 and 0. Hence our solution value, which is b again, multiplied by x sub b is equals to x sub b is equal to 77. Same as in x sub 6, in its solution values is equals to 80. Our key row is x sub 4 is the x sub 4 row, and our pivot element is 10. In table 2, our key column is the x sub 1 column. The minimum, which is 100 over 10, 77 over 7, and 80 over 2 is equals to 10. Hence our key row is equals to our key row is the x sub 4 row, and our pivot element is the 10. Hence in this, the x sub 4 departs and the x sub 1 enters. So the values here in table 2 are now changed. As you can see, in x sub 2, there are x sub 2 up to x sub 4, there are rate changes. In x sub 2 column, we have in x sub 2 row, we have 1 fifth, 8 fifths, 18 fifths, and negative 3 fifths. And in x sub 3, we have the 1 10, 13 10, 4 fifths, and 1 fifth. In x sub 4, we have 1 10, negative 7 over 10, and negative 1 fifth, and 6 fifths. For our x sub 5, we have 0 1 0 0. And for our x sub 6, we have 0 0 1 0. Our solution values are not interchanged. They are all still intact, which are 100, 77, and 80. For our table 3, our key column is still the x sub 1 column. Our minimum, which is as usual in the table 2, 100 divided by 10, 77 divided by 7, and 80 over 2 is equals to 10. Our key row is still the x sub 4 row, and our pivot element is equals to 10. Hence, there are now changes in our data. In the x sub 1 row, we have 1 0 0 0. X sub 2, we have 0 1 0 0. In x sub 3, we have negative 1 over 16, 13 over 16, negative 17 over 8, 11 over 16. For our x sub 4, we have 3 over 16, negative 7 over 16, 11 over 8, 15 over 16. For our x sub 5, we have negative 1 over 8, 5 8, negative 9 fourth, and 3 8. And for our x6, we have 0 0 1 0. So our solution values in table 3 are now changed. The 177.80 are now 73 over 8, 35 over 8, and 177 over 4. An optimal policy is x sub 1 is equals to 73 over 8, x sub 2 is equals to 35 over 8, and x sub 3 is equals to 0. Thus, the associated optimal value of the objective function is z is equals to 12 multiplied by 73 over 8 plus 3 multiplied by 35 over 8 plus 1 multiplied by 0 is equals to 981 over 8. And we have all finished our sample word problems in this topic. I hope you learned something in this video. Thank you for listening, and God bless.